Hello everyone. Today we have the pleasure of hosting Hongyan from University of Hong Kong, and previously OpenDriveLab in Shanghai AI Lab. His research is focused on autonomous driving and more recently embodied AI. He famously led the end-to-end driving project GenAD, or GenAD as some of us call it, which won the Best Paper Award at CVPR 2023. He is also known for a lot of impactful work in self-driving. For example, you might have heard of BEV former, however you call it again. He is also serving as area chair in our conferences like CVPR, NeurIPS, iClear, and so on. He organized many competitions, many impactful competitions as CVPR workshops or other conference workshops on autonomous driving. We are very happy to have you here today, Hongyan. Thank you very much for accepting our invitation. Today, he's going to talk about Vista, their recent work in autonomous driving, again, a large video data set. We are looking forward to your talk. Thank you very much.
Sure. Thank you, Fema, for the nice words. I really appreciate. And hello, everyone online. Unfortunately, I cannot travel too much. So I'm here sitting in my office to introduce you guys a few advances or recent progress from our group or from the community on the topic of autonomous driving. So you can see my slides, right?
Yes.
Yeah, okay, sure. So the title would be on the topic of auto driving, and although it can be extended to other topics like what we do here for robotics or other applications for the moving part. So the title is Evolution of Mobility, or how to say that. So how far is it away from achieving the AGI or the general intelligence of driving in the application in the future ahead. So the outline of my talk today will consider three parts. The first one is a little bit introduction for the topics that we are going to cover. And then we have like one work in central, which is the Vista. So basically it deals with video prediction work, and it achieved the controllable and high fidelity, or to achieve the realistic appearance to generate a lot of videos in the environment. So using the technique called the word model. And the last part is some concluding remarks on what the challenges out there and maybe some future directions in this area. So the first one is, so this is an autonomous driving topic. We have basically three very essential parts. So the first one is data collection, right? You need a massive amount of data to tune your model. So we have a lot of expert driving to collect those realistic data. And once we have that, we have a training infrastructure, whatever you do it on a workstation or on a data cluster. And we are going to train on some fixed log replay, which means so the data is, once the data is collected, so the behavior or the driving logs are fixed, right? And then we have to evaluate the model we trained. So basically, we rely on the human monitoring or intervention to see how the model performs. And through a closed loop feedback, which we identify certain critical cases where the model fails, and then collect some specific scenarios for the bad cases and retrain all over again to make a very shapeable pipeline for the whole procedure, right? So the issue is, so the current framework heavily rely on physical interactions from in the real world. And it also deals with the resource consuming, which means the data collection is highly luxury if you label literally every object in the same. And also we have the domain restrictions. So basically it cannot generalize to new environment, things like that. And also it deals with the safety concerns, how can it deals with the alignment with the human driver experience. So how to confront with this, especially for the very challenging auto driving problems, because we are in the stage, we are currently in a status that the whole community, I mean, globally, most of the perception problems or most of the issues have been well resolved, right? We have seen very successful cases in the Tesla cars, in the Huawei cars. They have already shipped with some stable or some nice results. And so what's the next generation of autonomous driving given the current progress in the community? So in this work, we are going to argue that we want to achieve the goal of reduce the cost for deployment. And also we want to have a interactive environment, which means, for example, given the current actions or prompts, we need the environment to interact, to respond the results the model has output. And also we need to design some scalable evaluation where it can fairly evaluate the output, for example, of the word model instead of some video generation qualities in terms of NSR, for example. So given this background, so there are some possible solutions given the current state of the art. So we have like this work called the street view generation, but it doesn't have any dynamic agents. So basically it reconstructs the whole scenes in the driving cases. And also we have the graphic engine option. For example, the Kala, and also Kala is very famous for auto driving interaction, especially for the closed loop evaluation. But it also bears with the sim to real gap. And also for the neural rendering part, so someone may argue, okay, we can utilize the neural rendering techniques to generate the scenes in the environment, but it also suffers from the poor scenario generation. So all this work struggle to represent the complex dynamics and diversity of the real world. So in this world, in this work, so we argue the word model might be a effective solution, which means so by definition, word model can predict future state based on previous states and current action. So basically, it's a probabilistic output likelihood given the current environment. By seeing environment, you can imagine, you can say it's a image or it's a latent embeddings or a feature input. And also it's conditioned on the current actions. Say, for example, open the door. So you see the environment and you imagine what's gonna happen after you open the door and generate the environment onwards. So that's a very plain explanation for the word models. And it's proven to be effective in various domains. We have seen similar works from the Google team, like what they do for the simulated gaming, for example, the Dreamer series work. And also the we see applications for the real robots. So we list some references in the bottom part of this slide. So we want to argue, how about to utilize the word model concept in the domain of auto driving? So what if we build a driving word model at scale? So the data can be scaled up, and also the applications can be scaled up as well. So so the problem setup is large scale real world driving data. We have a lot of driving cases and logs, and we want to achieve the video prediction given the current, for example, the actions turn right, turn left, and we have the real world dynamics. And we want to achieve the zero gap between the simulation to the real world scenarios. And also we want to achieve the generalization part. So how to do that? So we want to try in terms of three terms, I suppose. So the first one is we want to utilize word model to generate synthetic driving data. For example, utilizing NERF and also 3D Gaussian splatting, things like that. And also utilizing the word model can achieve the interactive learning by given the actions to interact with an environment. And also, if we design sort of a reward, for example, how to evaluate the generated environment, or is it in a form of L2 loss given the predicted trajectory with the ground truth annotations. So how can we evaluate via imagination the quality of the word model? So in this case, we will replace each component with the word model. But just to be sure, so those are three very long-term aspects. We are not arguing that in the Vista work, we have already fully resolved those three aspects. But instead, I think in order to help the future, like the so-called next generation of driving paradigm, so we can have a few attempts in these three aspects. So to be specific, we have this work called Vista. So it basically tries to resolve or answer the question on how to build an applicable driving word model. And it's a recent work. So so here are some background. So we have the limitation of previous driving word models. So some are focused on the generalization part, but it has a limited data scale and geographic coverage. For example, if we do it on the new scenes, it only covers 2 cities, Singapore and Boston, with 5 hours. And also some work, it bears some small resolution input, so it doesn't have enough representation capacity or the inferior fidelity, things like that. For example, the Drive Dreamer and also the Drive Word model and other work. And also, some work doesn't have the action control, which means it relies on the single action modality, or it doesn't have a zero-shot action controllability, which means so previous work doesn't account for like the steering or acceleration or the signals from the canvas to make a diversity of multimodality, because those are essential signals to guarantee a stable and better performance towards the trajectory prediction. And also how to utilize the word model. So I think this part, so the 4th bullet point is the most underexplored area that the whole community doesn't put too much effort on. So in this work, we argue we have collected or built on top of the GenAD work to have the worldwide generalization, and also we have the high fidelity by making like a few modifications to make the word model or the foundation model we generate to have higher resolution output. And also we have the versatile action controllability, where we utilize a high-level command or the waypoints output. And also we have the low-level trajectory or angle or steering command as the input to the system. And also for this part, to be honest, we haven't explored too much on this part, but at least we gave a little bit insight on how to design the generalizable reward function, because so thinking some applications only in that way, so the word model can truly be applicable in the real products, right? So yeah, and as for the first part, so this work is the prior work before the Vista work is called a generalizable predictive model for autonomous driving, which is published in this year's CPR, and we construct the largest public driving video data set. So it's sourced from the YouTube, and it is easy to scale up. So to give you a very specific comparison, this is the training data in terms of hours. And the gray part is the private data that you cannot have access on. And the blue part is a public data set where we can see, unfortunately, for the negative part, the public data are all very small scale. And these work are all based on the nuisance part. And we also see some work from the NVIDIA, from the Tesla, from the Wave. They construct their own data corpus on the training part. But instead, we collect the data from the online. Those are all the first ego-centric view. So although there are many driving data out there, but what we need is some camera mounted in the front glass of the car. And we want to build a like ego-centric view of the driving scenarios instead of some commercial advertisement where you can have the driving scenarios from some drones. That's not the case that we are gonna have here. So after a lot of sanity check and some quality check, so in all together, we have like 24,000 of hours of the driving data set. And I suppose almost over 1,500 of hours are from the YouTube, and the other a few hundred of hours of driving data are from the nuisance, from the Waymo, things like that. And also for the geographic labels, we just extract the meta data from the information that the user has uploaded and sparse all these meta data. For example, the city names, the other the labels from that, and to draw this statistic figure. So for the Vista work, we built from the model called the SVD. So it's so the SVD is a video generation. It's not for the future prediction, which means it builds on the condition frames. But because it's a video generation, right? It doesn't consider the data distribution. So our objective in this Vista work, we have this coherent future prediction in the long horizon. So basically, we means so the data distribution has to be aligned with the first frame. But in the video stable video diffusion framework, it can generate arbitrary styles and things like that. So because the objective is different, in the driving cases, we need to guarantee the coherent generation of a consecutive future frames, right? But for the video generation, it's more like a generative AI content where you can create like the artist contents, whatever you have, right? So the goal is a little bit different. So to secure that, how to achieve the predictive part to make the coherence between different frames. So there's a very important modification on that. So we built on top of SVD because it has a better performance and it is easy to fine tune things like that. So we have the initial frame as the conditional image, which is shown as a blue part, as a green blue part. And also we have inject multiple condition frames as the dynamic priors to enable this coherent rollout. So basically we have these dynamic priors, replace them to append them as the initial input and do this autoregressive rollout in the Vista model to secure the coherence. This is the first modification. We swift from the video generative model to a predicting model. And the second part is improve the fidelity. So by seeing fidelity, we want to improve the resolution size as to the video generation output. So because we argue the dynamics critical regions For example, the critical regions among, for example, the edges, they only occupy a rather small area, and you have to capture that. How to emphasize this part? So we want to highlight the motion disparities between the prediction and the ground truth. So here, this is the prediction between different frames. So we capture the prediction of motions. And also we have the ground truth frames, right? So we have this weight to emphasize the dynamic aware weights in terms of the motion. And also we impose this weight on the original standard diffusion loss. So this is a modified dynamics enhancement loss. So by doing so, we can see this is an example, although it's in a static form. So this is a static frame. So without this modification or the modification of the loss, we can see the front car doesn't change. It doesn't change at all, right? But with this dynamic loss modification, so the front car becomes smaller and smaller, right? So we can see this enhancement is quite obvious. Okay, this is this part. And also the second point as to improving the fidelity is we want to extract the faster moving objects because they tend to result in a blur or corruptions. So how to alleviate this? For example, we have a high moving object in these cases, or in the very far away region of the scene. So we can capture or enhance the high frequency structure information by using like extract the edges of lines. So this is a very common practice, as we have a high level filter by utilizing the Fourier transform and using its inverse form to impose a feature learning of the representation. So we have the original frames. This is decoded high level filter features, and then we can capture the very high frequency part of the scenes. So to summarize, we have those important modifications, and this slides we shown here is an effective learning scheme. We have a two-stage learning to acquire different capabilities. So the first stage is to emphasize the generalization part, where we build on the large-scale data set I just mentioned. We have the video input, and the Vista here is to train all together and generate the video output. And the second stage, we want to emphasize the controllability part. So the first one is built on top of the large-scale collected data set to guarantee the model has seen a bunch of diversity of the driving cases. And the second part is built on top of the new things, because we have this controllability problems. We want to secure it's given different dimensions of input. For example, the actions, the low dimension of actions, the high level targeting goals, things like that. So the second training phase, we have the actual input, and also we project in forms of latent embedding, and only fine tune this part and using the LoRa technique, and have the video prediction output. So the very key thing is unified conditioning. We enable versatile action modalities. So basically, we have different sources of input and concat them all together and use the zero init projection to the system. And the second takeaway is the data compensation. We want to leverage different data sources, right? So given the large scale unlabeled data corpus, right? We also have some scarce high quality of labeled data. So that's why we split the whole training pipeline into two stages to sterilize the training and also guarantee the requirements we mentioned in terms of controllability.
Hongyan,
So
do you have
this,
any questions during talk or after the talk?
yeah, I can take whatever either way. Yeah.
I was curious about like multi-view in new scenes here. Do you only use frontal camera or do you use other cameras as well?
I believe we only use the front view camera input. Yes,
But
because
Mhm.
yeah, sure.
It could be conditioned on the camera viewpoint, right?
Yes, yes.
Okay.
Yeah, I believe for the new scenes we also use the front view only. Yeah.
Okay.
Sure. And as for the capability, here are some results. So this is a comparison of prediction fidelity on the nuisance validation set. So we can see in terms of resolution, Vista achieve a very high resolution based on the modification, and also up to 15 seconds. I can see that. But for some may argue that for the Sora, it can generate at most 1 minute, right? But in the driving cases, it's highly challenging. And also, someone may doubt whether or not it's necessary to generate 1 minute of video part. Okay, and there are some visualization part. So we can see Vista can generalize to open scenarios, and also it achieves the coherent long horizon rollout. And also, if we make some action, like to tell the scene to turn left or go straight, so all these so all the columns are based on the same initial frame. So if we give 4 actions, we can see it can generate different imaginations based on the actions being given. Okay, and as for the very last application part is the reward function. So we have some observation here. So the first one is Vista is trained on human driving videos, right? And Auto's distribution action condition will increase the prediction uncertainty. And based on that, so the prediction ability of Vista itself, I mean, once you have this model itself could be used to evaluate the actions. So without resorting to ground truth trajectories, you cannot even bother to compare with the ground truth annotations, or it can also inherit the strong generalization ability because you trained on the large scale data. So maybe reward estimation is the cornerstone for RL, right? Because how to design the reward application is a very important thing to employ the reinforcement learning stuff. So, but in this work, we are still investigating. So in this work, after you have this reward function, how to utilize this reward, or how to, like, for example, does the reward can be utilized as a new metric, or the reward can be utilized a confidence score to output the trajectory output is still underexplored. But we would argue that how to design this reward part for the word model is a very challenging part, even in some applications. For example, the Unisim from the Google Mind team, they haven't explored this part as well. So to sum up, we have our recipe here. Basically utilize the large scale real world data to secure the generalization. And also we have the video diffusion model to achieve the realism, where we have the goal of realistic visual appearance and motion. And also based on the multi sources of input, we have created this multi-model setup to secure the controllability, where the model output is controllable by different actions and human intentions. And as for the future work, so today's topic is more like the using the word model to facilitate the auto driving, especially for the planning part. So we did a little bit of literature review in this community, and we see in the early years, we have these word models. I think this is a newest paper in the early days to model RL environments. And also we have this Dreamer series work. It basically built the system towards generalized agents and the scalable word models in the gaming, in the simulation, in those areas. And also for the video space methods, for this part, for the green part, basically the technique is very simple to create realistic scenarios with a very large scale data set. We have seen this UniPy, Unisim. It's based on the action or goal controllable universal the video generation. And also the Gaia work, right? So basically it's a very early work working on the also the driving video generation. And also the DriveDreamer, GenAD, and also the Vista. And also recently we have seen the 1X word model for real-world humanoid robots. So you can imagine, right? So this whole pipeline to generate the future predictions or future imaginations is also very feasible in the applications of robotic tasks, where you can interact with the environment. But we bear very different characteristics, right? So for the driving part, the space is very large and the scene variation is very distinct. But for the robotics, the tasks are very challenging in terms of you have a very large number of degree of freedom, right? Action output is very complicated, but the basically you deal with a very small space, like most of the tasks are performed for indoor applications, right? And another part is the latent space methods. So the upper level, the upper part is to generate direct video or image output. But for this lower part is to optimize the latent feature embeddings. For example, in the precision paper written by Yan Kun, it says the word model aims at to understand the world and rehearse in mind. And also we have the Java series work and also the WIDA or latent word model. So basically, it will predict the latent embeddings given the text of word models. So I would say these two parts are parallel to each other. I'm not saying to advocate or endorse whichever ways. They all have these very well-motivated incentives. So we can basically have different future directions for sure. And there are some missing directions we think. For example, in terms of video word model, how to achieve the scalability and how to incorporate the causal reasoning, right? So all the things are based on the reason from the past to predict the future, right? And how to use the word model in a closed loop setting where we have all the simulation with the environment, given the feedback from the prediction output, right? Otherwise, the algorithm we design is not interact with the environment. So that's why we define in nowadays the community focus more on the closed loop evaluation because those are 100% to the realistic cases for the deployment, right? And also for the 4D reconstruction, there's a recent work, I suppose some of you guys may know, from the Wave team, where they have this prism to predict very realistic video generation. So it has explicit representation, at least from their blog, because they didn't write too much technical details. And so it's very intuitive to obtain cost. I mean, the cost from the bounding box or some, because you can manipulate each object in the scene, right? You can design the cost or the reward, whatever we have. So given those two trends, can we develop some like 4D word model. By saying 4D is not only in the expansion of the time, and also it's expansion into different forms. For example, the explicit design as to the environment, whatever the static or the moving objects. And also how to improve the reasoning over causality. So here we are going to show a few failure cases from our research work. So for example, in this case, we have like, so as you drive along the way, there are more vehicles just appear without any reasons. So this is absolutely insane for the realistic applications, right? And also in this case, so the right light is in front of us, but the car doesn't stop. And also how to embed the physical constraints into the model, right? So these are some results from the Sora work. And also we have this case, how to enable multi-model representation with scarce paired data. For example, how can we utilize different sorts of data? For example, in the domain of robotics, can we secure the erectile sensors to sense different types of forces, right? Or how to incorporate the depth information or the flow information to better utilize the multiple sources of the information in the environment is also very challenging part. So I think those are basically all the challenges or some issues to be addressed, I think, by all the community efforts. So there are some takeaways. So a word model as the last part or a very important bottleneck for the next generation autonomous driving development. And also we can transform the video generation model to word model where some effective modifications, whatever, we try in the data composition between the pre-training large scale data to some domain specific data like new things. And also the learning state scheme, we have the two phases training, for example. And also the last part is a challenge still remain in improving the word model from multiple axes, which need the community to resolve together. Okay, so basically that's all for my talk, and my huge thanks to my team, especially the author from Jiazhi, from Shenyuan. They are the first author from the GenAD and Vista. Some students are in mostly, I could say, in Shanghai, and we have also some students in Hong Kong. So basically, thanks to them for the slide credit. Yeah, and I'm happy to take a few questions.